My name is Amina Hussein, and I'm an assistant professor of electrical and computer engineering at the University of Alberta. My lab uses high-power laser systems, and we apply these to a diversity of topics. We look at the conditions that are relevant to fusion energy reactors for virtually limitless clean energy. We also develop novel diagnostics for agricultural sensing, and we make compact particle accelerators. So there are two main schemes for achieving fusion energy on Earth. One is magnetic confinement fusion, and the other is inertial confinement fusion. In both, the game is to force together light nuclei, hydrogen isotopes, and to get them to overcome their natural repulsion so that they can fuse and release energy. In inertial confinement fusion, we use lasers to heat and compress a pellet of fuel so that we can have a fusion event. This is where lasers play a role, and this is the kind of fusion that my research group is related to. In particular, we use high-power lasers to produce these exotic states of matter that would occur at the core of the sun where fusion occurs, but doing it here on Earth and in the lab where we can understand and hopefully control it. In particular, we use spectroscopy to diagnose these states of matter, measure, in this case, their X-ray emission, and use that to untangle the physics that's occurring so we can get some fundamental information about these interactions, and later on apply that to optimize these events and achieve fusion energy systems.
So in these high-intensity laser plasma interactions, we are interested in studying the high-energy particles and photons, or light, that is being generated. These plasmas are generated by shooting a inconceivably intense laser onto a solid target. So like you can imagine a thin copper foil or a thin aluminum foil. And the laser is so powerful that it will immediately rip all of the electrons around the atoms, the copper atoms or the aluminum atoms, and it creates kind of like a hot, dense soup of plasma.
The really cool thing about lasers to me is how versatile they are. So part of what my lab does is we travel to large-scale laser facilities around the world to do these experiments, but we're also using smaller-scale lasers closer to home for completely different and maybe more down-to-earth applications. Right now, through support from Alberta Innovates, we're developing a portable laser sensor for measuring soils in the field. The goal here is to address the need from farmers and from our industry partners to be able to analyze soils in real time and in the field. Currently, soil analysis is done digging up soil, sending it to the lab, doing wet lab analysis that can be destructive, and then bringing back the results, which can even take weeks. With a laser and using a technique known as laser-induced breakdown spectroscopy, we can shoot the laser, hopefully right in the field, onto a sample of soil and get our measurements through spectroscopy instantaneously. The aim here is to provide real-time, high-sensitivity information about these soils that can inform crop yield, fertilizer application, what you're planting, and give farmers a lot of control about what they're doing in real time.
The real-time soil analysis is important because if you want to optimize the fertilizer, or if you want to see due to the global warming how our environment is changing, especially how it's affecting in the cultivation sector, we really want to know in real time how every nutrition, for example carbon, nitrogen and phosphorus, is changing. So the portable system will enable this technology. Farmer or any soil analysis company can do real-time soil analysis.
What I find really fascinating about this work and really rewarding is the ways that we can take these technologies and translate them into everyday, relatable and important applications and topics. And it's really great to have students that come on board and are motivated by these topics and applications as well.